We proved this theorem last time. It says that an extension k over f is finite if and only if you can get k from f by adding finitely many algebraic elements. And more generally, if you can get k by adding a bunch of elements such that if you take the tower obtained by adding them one at a time, like this, then A1 is algebraic over F, A2 is algebraic over FA1, A3 is algebraic over this one, etc. So I want to get some corollaries out of this about algebraic extensions. The first one, up on the right, says that if you have a tower of extensions, we write F contained in K contained in M, and if you know that K over F is algebraic and M over K is algebraic, then the big one is also algebraic. How does this go? I'm gonna make this a little bigger, probably it will help. So the way we remember it is we say algebraic over algebraic is algebraic. Note, we know already that finite over finite is finite. In fact, the dimension of the vector space just multiplies. Oops, this is M. So how do we show that M is algebraic over F? It means that you give me any element in M, it satisfies some non-zero polynomial with coefficients in F. So take A in M. I don't know that it satisfies a polynomial with coefficients in F yet, but I do know that it satisfies a polynomial with coefficients in K. So let's find such a polynomial, because M over K, remember, is algebraic. Since M over K algebraic, we can choose some polynomial with coefficients in K, non-zero polynomial, such that P of A is 0. Let's write out this polynomial. We can take it to be monic, doesn't matter. You can always scale the top coefficient to be 1. So this is what a top polynomial looks like. I want you to notice that a polynomial only has finitely many coefficients. These are elements in K, A0 through an minus 1. A0 through an minus 1 are some elements of K. Some of them is non-zero. All of them cannot be 0. No, I don't even care about that. I took the top coefficient 1, so they could be 0. So they're elements of K. Let's just add those elements to F. And this is the crucial observation, that A is already algebraic over this field, which is potentially smaller than K. So note, this polynomial actually has coefficients in K prime. Because this field already contains all the coefficients of this polynomial. That's how we build this field. So A is algebraic over K prime. So if you take this extension, this is some subfield of M. So k prime A over k prime is finite. We know what extensions obtained by a single algebraic element looks like. They look like this on the left. Still have that theorem. It looks like the polynomial ring modulo the maximal ideal. So they have degree finite. It's the degree is equal to the degree of this polynomial, of this minimal polynomial. On the other hand, so this is finite. On the other hand, by theorem, a theorem that we proved last time, this extension, f is 0, an minus 1, over f is also finite. Since all these guys, a0 through an minus 1, they live in k. So k over f is algebraic, you see. So these guys are algebraic over f. So if you take an extension obtained by adding finitely many algebraic elements, that's an algebraic extension. Now this is finite, that is finite, and compositum of finite is finite. Sorry, a tower of finite extension gives you a finite extension. So k prime A over f is also finite, hence algebraic. So A, which lives in k prime A after all, is algebraic over f. This is a rather lovely argument, and it's rather indirect. And this fact that a polynomial only has finitely many coefficients keeps on playing out over and over in this theory. I have a second corollary here. It says that if you have an extension k over f, and if you have two algebraic elements in the big field, then their sum, product, inverse are also algebraic. I mean, the inverse is very straightforward. I mean, inverse if A is non-zero, of course. Let's see why this is so. So I have k over f. Let's clean this. And I have A and B in k, each of them algebraic. So you look at these intermediate fields, which is same as if A and then add B. See, A is algebraic over f, so this is algebraic. B is algebraic over f, so B is algebraic over the bigger field as well. B satisfies a polynomial with coefficients in f. So of course it satisfies a polynomial with coefficients in fa. Any polynomial with coefficients in f is also a polynomial with coefficients in fa. Just like any polynomial with rational coefficient is also a polynomial with real coefficient. Having a big field is fine. A bigger field is fine. All I mean is f is contained in fa. So any polynomial with coefficient in x is also a polynomial with coefficients in fa. So B is algebraic over f. So B is algebraic over f adjoint A. So this is algebraic and that is algebraic. But that tells you that the big extension is also algebraic. Also, fa over f is algebraic. So by the previous corollary, you get that the big extension is also algebraic. Meaning every element in this fab is algebraic over f. But you see, these guys do live in that big extension. this one if A is non-zero. These guys all live in the extension FAB, because A and B do live in there, since FAB and FAB is a field. So again, this is rather indirect. You are given, the condition is that you're given that A and B satisfy some polynomial with coefficients in F. And you want to find some polynomial that A plus B satisfies, some polynomial that AB satisfies. This doesn't quite directly tell you how to find that polynomial. It sort of takes a very indirect route. For A inverse, it's straightforward. I mean, if A satisfies this equation, if A satisfies a polynomial equation, something like this is 0, and let's assume A is non-zero, then you can just multiply by A to the minus n, and you get A 0 times 1 over A to the n plus A1 times 1 over A to the n minus 1. So there is a polynomial that 1 over A is satisfying. Yes, that one is very easy, but for the other ones, it has some content. And the immediate consequence of this is part B, that the set of all elements in K that are algebraic over F form a subfield of K. So you have K and F, and here we have, maybe let's call it A, elements of K that are algebraic over F, meaning the elements that satisfy some polynomial equation. Because if you have two elements here, both of which satisfy some polynomial equation, then their sum is also there, their product is also there. If it's non-zero, then the inverse is also there. So this A is a field itself. And this is also not at all a priori clear. I mean, so you're getting some rather non-trivial statements here. I want you to realize that, for example, if you take the complex numbers, it's an extension of rational numbers. It's a very important object to look at, this field of all algebraic numbers. So these are all complex numbers such that they satisfy some polynomial equation with rational coefficients. This, we see, these numbers are called algebraic numbers because they satisfy some polynomial equation with rational coefficients, so you can actually clear denominators and you can actually say integer coefficients. So this is actually a field. That's what this corollary is saying. This is called the field of algebraic numbers. So like rational numbers are algebraic numbers, but so is root 2 and root n and 2 to the 1 over n and all these things, and e to the 2 pi I over n and root 2 plus cube root of 5 and all these things, and lots of other things that I cannot even write in this way, whereas these are in A, but things like pi and e are not in A. So this A consists of basically all solutions of all integer coefficient polynomial equations. So it's a very central object of study in number theory. The study of this extension consists of very many beautiful results, and it's much of algebraic number theory. So we'll move on to talking about splitting fields, but before that we have a little bit of definition. I mean, to talk about compositum of two extensions for a little bit and introduce embeddings of fields, and then we'll move over to splitting fields.